Hello everyone, in this video we'll try to demonstrate what is the minimum level of boron concentration we can get in a WWER-1000 Russian reactor, and to see if the security of this reactor can be compromised by the very low boron concentration. I will start the simulation with rated state operation 1 log, so 100% nominal power, and fuel in BOC, so beginning of cycle. The fuel rods will be the maximum enrichment in uranium-235. So the point is to see if we can reach criticality just by reducing boron concentration in the moderator, and if this happens, obviously this will seriously compromise security, because we can not reduce chain reaction by introducing rods, because rods are already totally introduced. Sorry, I forgot to say, I will start this rated state operation, but I will create a scrum, so we will have a totally inserted rods situation with a hot reactor. So let's start. Okay, we see the nominal power 99.9, boron concentration 7.5, and we see the enrichment, it's 4.2%, so this is a totally enriched fuel. It's the beginning of cycle. Now we create the scrum. Sorry, the simulation was not running yet. So first of all, I switch on the simulation. Now we are running. We see some decimal points changing here, and now I press the scrum button, and we have the scrum. We see the buzzer totally inserted, boron 7.5, and now I will use this trick that I already used in a previous video. So let's disconnect the relation between the 1C model and the boron shim, set it into auto, and let the boron concentration decrease. In the previous video I already did this, but I stopped it at around 4, if I'm not wrong. So here I will just see how low I can go. If the auto setting stops decreasing it, I will go to the manual and keep decreasing boron concentration. I can already remove this scrum button. And we will just wait for the moment. We're at 6.9, and we see the neutron activity going down to exponent -1 at a period of -27, very fast. We are getting alert, mainly because of pressure and level of steam generators. Of course, MSIV closed. In a normal scrum procedure, you will get all the rods inserted, and at the same time you will get the turbine disconnected from the grid. So here we have the turbine, we went offline. We have here steam generators with a level alarm, not real alarm, but not at the optimal value. Okay, and boron concentration 6.2. We see that the period is getting a bit higher, so we are in negative. It means we are decreasing neutron activity, so getting higher in a negative period, it means getting more positive, let's say. And the boron going to 5.9. That's good. And we see this very nice thermal production color scheme which is in relative scale, of course. Otherwise, everything will be blue here because we're at exponent minus 2, 0.0 of total nominal rated power. So because this scale is adjusting, so the most red dark red is the maximum value present in the reactor, and the dark blue is the most negative value. We also have this very beautiful colorful scheme. In some way it is similar to finite element outputs, in which you always get the scale to fit it to maximum and minimum stress values or whatever values you are computing in finite elements, so they always look super nice. Even if you have an homogeneous solution, they will plot just numerical noise and it looks super nice. Okay, we're at 5.1 in boron concentration. Now we start to be close to the value we got in the previous simulation, which was 4, and we had 4 minutes of simulation. Reactor getting more and more cold in terms of neutrons. I'm not talking about temperature. Temperature is 276 degrees Celsius, and this is not expected to go much lower because to get this cooled down we need to wait for many hours. This is a big volume of water. Even if you are not producing heat, it will keep the temperature for a long time. So we are at 4.5 in boron. Let's remember the previous simulation. I reduced the boron to 4.0 more or less, and then I stopped the boron shim. Oh, okay, it stopped already because we got a reactivity of 0 and it stopped reducing the boron concentration automatically. So now I will go to the manual and continue manually. So last time we stopped more or less here, and then I start withdrawing rods to bring the reactor up to power, and I just need to withdraw the groups 1, 2, 3, and the group 4, if I'm not wrong, I was at like 50%, so 3.5 groups were withdrawn to reach nominal power. So this is really amazing because we did the hot shutdown and restart in just 20 minutes. Actually, I think it could be done with a bit less time because I lost some time just checking parameters and things. Maybe with 17-18 minutes it could be done, and this is really fast operation. So I just want to see how far I can go reducing boron concentration, but I see now it's becoming really slow. You see the numbers going down, 4.353, so only the third decimal is moving fast, and we see a positive reactivity of 0.1. I don't know why it's this. I'm not an expert on this nuclear technology, but I guess because of the temperature going slightly down. Not really sure. Okay, look at the period. We got a 20-second period. Okay, and we got a 4.5% of power. So we really got to a almost criticality. We're not critical because I stopped reducing boron and we are already going up in period, but I will continue a bit. So now we can already tell that a boron concentration of around 4 point something with a BOC situation, so beginning of cycle in fuel, it's close to criticality. So let's see if we can bring this up to power just with boron concentration with all the rods inserted. Now we're at 6.3 of rated thermal power, so very soon I will go to check all the alarms and connect back the turbine to the grid. Okay, let's go to this tab, remove the scram alarm, blinking the block, and we just got the MSV and the level of the steam generator. So I think I can connect the turbine. Just click to auto and let's see if it goes online. Yes, it goes online. That's very good. That's very good. Going up to 6.3% of thermal power, and we can continue removing boron. We're getting a period of 60 seconds, 50 seconds, 40 seconds. Okay, we are stabilized at 44 seconds while reducing the boron concentration. We're at 4.15 and the power is at 11% of the nominal thermal power. That looks really promising. Really promising because we are already on grid, we are producing electricity, we are already at 14% of thermal power, and the period looks totally okay, around 50. We are close to criticality. So let's continue to see how far we can arrive just with boron, and maybe at the end we'll touch some rods to adjust the last percentage to reach the rated power. Okay, now the period is going a bit high. We're at almost 20% thermal power. Yeah, definitely it's going very high, the period. "130 seconds, and we are at 20% power. We almost reached 4 concentration of boron of 4, and right now we're going below 4, 3.999. You can see how the thermal activity is high in the center of the reactor. I would say this is a bit different from normal operation in which you have a roll-off in the corners, but you have kind of flat appearance. Let's say from the rod 2 to 9 or 3 to 7, more or less all the fuel assemblies have a similar thermal production, but here we have kind of peak in the center. I cannot explain why, and I'm not even sure what I'm saying makes any sense, but that's what I feel. Okay, we're at 28%, 29% of thermal power, 3.8 boron concentration, and the period getting higher and higher, 180. So I think I will need to stop the boron shim. Not that I will need, but I think I will do, because if we continue like this, it will get a bit longer to reach criticality. Maybe I should not say criticality, but to get to the rated power values of this reactor. And what I'm thinking also is that definitely I will withdraw the rod group 1, because you see that the outermost part of the reactor is the one producing the least heat. So definitely is the one that needs to be brought up a bit. Okay, period definitely going higher at 200 seconds. Boron concentration at 3.7. and we are at 37% thermal power. I really want to know what will happen, what will be the limit that we can reach with the just boron concentration. But probably to keep the video a bit not too long, I will stop at some point. Let's see a bit more. We're at 40% thermal power. Period 250. We can also have a look into the diagram of the fuel assembly thermal generation. We see the EIC 1, 2, 3 surrounding the pressure vessel. These are neutron detectors that are not inside the vessel, so they only come to action after a given value. I'm not sure if it's like 5% or so, but when we have a really low neutron activity, they just measure 0 because they are outside the vessel, so they receive less neutrons than the sensors we introduce into the water inside the vessel. Okay, the period is going higher and higher, 270. And very soon we'll reach half of the rated power of this reactor. 50%. As I said before entering the simulator, this is a very unsafe situation because of any reason we need a scram now. We don't have any rod clearance to introduce them more, they are already totally inserted. So basically the only thing we can do is to inject boron into the reactor, but the boron injection takes some time, it's not instantaneous. So I'm not sure if we were at 100% power and there was something like a turbine disconnection from the grid. I think the bypass can stand like 50% of the thermal power coming from the reactor, so we would need to reduce 50% of the power. I'm not sure with the boron injection that could be possible, and if we could go too high in temperature. But anyway, this simulator doesn't allow to test accidents, so that's just a speculation from my side. Here we just try to see how far we can go in power just with boron concentration. And we are at period of 320. %60 thermal power. In the previous simulation, I estimate that I could go back to 100% power in 18 minutes. We're at 16, almost 17 now. So probably I will stop at 70% of thermal power and then withdraw some rods to see how many groups we need. I guess just one group will be just fine. Group 1. We're at 69. 8, 9, and 70. I will stop and I will connect back the boron exchange 1C model. We see the boron is stable, 69.7, and we are going down. I don't know why. The turbine is working fine. We have, what do we have here? Why we have alarm? I don't see the reason. Anyway, this is fine. I don't see it, but it must be a minor thing. Okay, let's start withdrawing some rods. Selection to see in the plot what are we doing with the rods, and let's start. It doesn't look to be very fast for the moment, but it's the first group at the bottom of the reactor, so it's normal not to be very fast. Let's wait for it to reach 20 or 30%. It will have a much higher influence into the period. Period 300 seconds and going down quickly. And now it's fast at this. Look at the power 75. And the period is almost 200. Power 80%. Suddenly the period is going higher. There is some kind of oscillation here. There are things in this reactor I don't yet understand, like xenon concentration and some xenon and power cycles that I do not understand yet, but I hope to master them soon. Power 85%. We said the profile of the reactor is going, I mean, I cannot point to you with the mouse now, but if you look at the FA parameters frame and you see the horizontal histogram which indicates the activity of the fuel assemblies from 1 to 10, we see that it's biasing towards the bottom. So even if the maximum is at the 3, 4, it's biasing towards the number 1 because we are withdrawing group 1, and now we started with group 2 because of this mechanical interlock. Okay, we're at 95. I will release 1 second, and it's going down, so I need to withdraw, keep withdrawing. 96, 97. The period is not very low, it's around 300, so I can reach 100, I think, without problems, because the set point is at 107. Okay, I will stop here, and I will a bit more and try to get the automatic control. Okay, automatic control 99.9. We need to withdraw completely the group 1 and the group 2 until 23 for position 2. And we saw that the boron concentration, it took us like 17 minutes to reduce it to 3.3, and below that the effect on the period was very low, so we just decided to switch to withdrawing rods. But now we are running at full nominal power with just one group, let's say 1.2 groups withdrawn from the reactor. So I'm not sure about the security procedures, but I guess this is illegal, because in case of we need a EP, so a scram, I'm not sure we will reduce a lot the power. So now I will try it. I will press the scram button and we will see how low it goes, this neutron generation or thermal rated power. Okay, 3, 2, 1, go. We saw the group 1 going down. Now all the rods are inserted and the power is not going down at all. Still 99.9, but that was possible. We see here 6.8 plus 1, so there is some problem in this indicator. Okay, there is a bug in the simulator, but now the power is at 70%. So we've reduced the power to 70%. The The turbine luckily is still online, because if not, the bypass will not be able to withdraw 50% of the thermal power of the reactor, and we are still at 70%. So in that case, there will be a 20% of excess thermal power in the reactor, and without any means to reduce it, other than injection of boron concentrate, which takes some time, this could create a catastrophic situation, like destruction of the fuel assemblies and maybe a local incident in which we lose a primary fluid into the contention. Okay, I hope this was funny or helpful or something. See you in the next video. Bye.